Oh shit. Oh, wait. Assam, come here. Do you see the problem?
What?
Watch, when you stick your hand in front of it, it lights up, and then it unfocuses when you get rid of your hand.
Oh, yeah.
So maybe if we put something in front, unless we put it closer, otherwise it's gonna stay dark, because the room's dark in the front.
Are we keeping it here?
Yeah, so we could do one of two things. Or unless you like hold it the entire time, but that's gonna be unstable. See, like if you stick your hand in front, it's gonna focus.
Auto? Does it have an autofocus? It focuses if like we look at the wall right here and not the presentation's too bright.
Does it light
so
up?
It makes everything dark. Yeah.
Wait, let me try. Do you have a cloth? Oh, yo, how about this? Can we zoom in on his face?
It's getting too cold.
It's spilling! It's spilling!
It's water.
Oh my god! Some.
Look like this is funny.
How far are we into that? Look, I zoomed on his face, so it's let's keep it that way.
Okay.
We can't focus on the camera or the PowerPoint because it's gonna get too dark.
Okay.
So is that good?
Let me see real quick.
Okay. Because if you try turning it slightly, it's gonna get a little dark.
Yeah.
Right there works.
Alright guys, listen up. We're going to begin the second part of our meeting. Please welcome the only material scientist in the MIE department, Dr. Abiade.
Okay, thank you. Didn't know material science was that popular. Okay, so I just titled this overview of LORA Research. That's the name of our research group, the Laboratory for Outside Research and Education. So with this presentation, I'm going to give you a little bit of information on my background, like how I got to this point where I'm now standing in front of you. I'll talk about material science, what it is very generally, and then give some examples of some of the material science work that we're doing in our laboratory. And I think you guys would be really interested. A lot of the work is being done by some of the TAs in your classes, so you get to see like what they're actually doing when they're not grading your papers, your quizzes, and why that might be delayed sometimes. Okay. So first, I always like to acknowledge people that I work with in my research because typically we don't do research by ourselves. So Dhananjay Kumar, he's at North Carolina A&T. I work with him very closely. Jim Thompson at University of Tennessee, Knoxville. He's also a staff scientist at Oak Ridge National Lab. Ashutosh Tiwari, who's at University of Utah. Senko always at the Korean Basic Science Institute. And also Scott Huxtable at BT and from Virginia Tech. And Aaron Stein at Brookhaven National Lab. And on the right, you see the students that have worked on this research in our lab. Chinlin Zhao and Gordon Waller, they were my students at Virginia Tech when I was a professor there. Chen Chen, Mohammed Asadi, and Riyad Asgayer and Sinpu Fu, they're graduate students here here at UIC. And of course, the students are most important, but close to important if we're comparing the students and the funding, we can't do the research without the funding, so we always acknowledge that. We've had a couple of research grants that have been funded by National Science Foundation, and also we've received some funding from the university to do some of this work. So, my name is Jeremiah Abiade. It's pronounced Abiade. That's how I pronounce it. Only 6 letters and 4 syllables, so it can be a little bit confusing sometimes. I'm an assistant professor here in the department. I joined here after being at Virginia Tech for 3 years. I was an assistant professor there. I had a joint appointment in the Department of Material Science. They had a standalone material science department there. And also, I had an appointment in the Department of Mechanical Engineering. So my college journey started in 1995 when I graduated from high school, which might seem really, really long time to some of you guys, because you guys are probably, some of you were probably born around that time, which is really scary. I graduated from high school in 1995, and I enrolled in Southern University A&M College in Baton Rouge, Louisiana, where I finished my undergraduate degree in physics in 1999. So Southern University is what's considered historically black college and university as part of the minority serving institution, network of minority serving institutions. UIC has recently joined that network because we have 25% of our undergrad population is Hispanic or Latino, so we're now considered Hispanic serving institution. So that's something that's new this fall. After being at Southern for 4 years, I had an opportunity to go to several places to do undergrad research. I went to Center for Advanced Microstructures and Devices. I went to Northwestern University, where I was in the Department of Physics, and I went to Vail Labs in New Jersey. Those experiences really got me interested in material science and doing a PhD in material science. So I went to University of Florida, the Gators, in Gainesville, Florida, where I did my PhD. I graduated in 2004. And then I did a postdoc from 2005 to 2007. So I graduated December 2004, started my postdoc in February 2005. And basically that's just additional training to prepare you for a career in academia, which is what I'm doing now. So you get more opportunity to hone your research skills, to make yourself distinct from your research advisor, publish a few more papers, and also you get opportunities to supervise students. And by the way, if you have any questions, feel free to stop me at any time. And then in 2007, I joined the Hokies at Virginia Tech. Woo! Came here in 2010. Okay, so the question might be asked, how did I get here? I was born on the south side of Chicago in Michael Reese Hospital, which is no longer here, but it's in the Bronzeville neighborhood, not far from McCormick Place. When I was born, my last name was actually Gray. I changed that when I was a graduate student. That's another story. So the question might be asked, how did I get here? Neither one of my parents had gone to college. Actually, my senior year in college, my mother was a freshman at the same institution. And my father, he went back a couple of years after I graduated. So when I was in college, it was me, my sister, and my mom. We used to have lunch together on campus. So my parents, they didn't know anything about college. They just said, you're going to go. You're going to have good grades in K through 12. That's not an option. So when I was in high school, I was pretty decent at math growing up. So people said you should be an engineer. I didn't know what that meant. I thought electrical engineering was like being an electrician. I didn't want to do that, so I'm not going to go into electrical engineering. I thought mechanical engineering was pretty cool. It's somehow related to cars and airplanes, so I said I was going to apply to Southern University, to the Department of Mechanical Engineering. So when I applied, there was this pre-college program for students that did well in high school. I applied to that also. And I listed my intended major as mechanical engineering. So one day, a couple of days after my high school graduation, I got a call from this person right here, Diola Bagayoko. He runs an academy at Southern called the Timbuktu Academy. Who knows what Timbuktu is? Where's Timbuktu?
I believe it's somewhere in Western Africa. Not
Mali,
sure
I think?
Yeah. Yeah, Timbuktu is a famous city in Mali. Typically when we say Timbuktu, or we use it in our common language, we mean it to denote something very far, right? From here to Timbuktu, like that's how we use it. Actually, it's not as far. It's West Africa, which is fairly close to us if we compare like Europe or Asia or some other countries. So Timbuktu is one of the well-known historical sites in the world. It's located in Mali, and here is one of the UNESCO heritage sites, the City Yahya Mosque. Basically, Timbuktu was one of the main learning centers in Africa. So this person, Diola Bagayoko, his family descends from the line of people that were teachers there for hundreds of years. So when he came to the United States, he has a bachelor's degree in physics and chemistry. He did both of them. And then he did a PhD in physics, and he decided that his mission was he was going to be a physicist, he's a theoretical physicist, but he was going to motivate minority students to pursue a PhD. So when I graduated from high school, he started this academy in 1990. In 1995, I graduated from high school. I got a call from him. I was asleep, actually taking a nap. I remember it like it was yesterday. It was like an afternoon. I get a call from this person with a really deep voice, very thick French African accent. He's like Mr. Gray. And so I thought it was one of my high school friends just playing on the phone. So I started to mimic back his accent. And so he, like I was just joking around with him. So he's like he has a very deep voice. It's like, young man, what are you doing? So I realized that it wasn't my friend. I thought it was my friend James, who always used to play jokes. And so he called me, he told me, I saw your record, it seems like you're a serious student, but based on this phone call, it doesn't seem like that. So I was like, no, I'm sorry, sir. Please forgive me, I thought you were my friend. You know, trying to make a bunch of excuses. So he was like, I'll give you another chance, come down to my office, I want to talk to you about something. So I went down to his office. I went to high school in Louisiana, Louisiana. So I went down to his office, and he told me, like, we talked, he asked me several questions, he asked me some technical questions. He's like, you seem like you're kind of sharp. I want to nominate you for this NASA undergraduate student award for research. So I was like, okay, what does that entail? He said, it's $12,000 in your pocket, plus they pay tuition, they pay housing, they pay books, they pay meal plan and everything. So of course, you know, I just told you about my family background. I said, what do I need to do? So he said, first thing you need to do is change your major to physics. I'm like, okay, whatever. The second thing you need to do is that you need to write a personal statement and apply to this program. So I was like, okay, when is it due? He's like, it's due like in a week. I was like, okay, I'll get it to you in 3 or 4 days. He's like, no, go to this computer right here and type your personal statement. You have an hour. And so I went to the computer, typed it up. He gave me some suggestions to improve it, and I applied for it. And a couple months later, I found out I got the NASA undergrad student award for research. So that's what supported me through my undergrad education. Until the first day on campus, my mentor, Dr. Bagioko, became my mentor. So he set me on the path to pursuing a PhD before I even knew that that was a goal that was attainable for me. Like before that, I thought you could only get a doctorate in medicine. I didn't know anyone that had a PhD in engineering. So I consider myself very privileged to have been a part of Timbuktu Academy, and it's kind of building on the legacy that his family helped set in West Africa. So here at UIC and also at Virginia Tech, I just graduated my last student at Virginia Tech this past summer. But we were running the lab in 2 different campuses. The name of our lab is Laboratory for Oxide Research and Education. And basically we focus on material science, oxide synthesis and characterization. We focus on electronic, hydrophobic, and thermoelectric materials. And we use a technique called pulse laser deposition to investigate these materials. So I'm not going to go into a lot of detail on that. I'll kind of highlight one of the students' research and then hopefully leave some time for questions and discussion. But I think you guys know several of these students. This is Abiade. I'm sure you guys have had him as a TA. He recently finished his PhD now. He's at Portland, in Portland, Oregon, working at Intel. This is Fu, who's the longtime TA for ME 250, and Mohammed Asadi, he's now TM for ME 380. All 3 of these guys are PhD students, or Riyadh technically defending his PhD, but he's going to graduate in December. And Chenmin Zhao is our PhD student that just finished from Virginia Tech. He works for SKF here in the Chicago area. I'm trying to get him to come to recruit the students from our department. Okay, so the question might be asked, what is material science and engineering? And, we can define them separately. So material science is the investigation of the relationship between the structure of a material and the properties of a material. Materials engineering is on the basis of those structural property relationships, is the designing or engineering of the material to produce a predetermined set of properties. Okay? So typically when we talk about definitions for material science and engineering, we invoke this paradigm here, the structure, properties, performance paradigm, right? So it's basically a cycle. Like you have your material, it has a certain structure that typically leads to a certain type of property that you can get a certain performance from it. And if you want to make a device or some system, you have to do different types of processing. But you can change the properties of the material and, of course, the structure of the material by the processing, and that's going to affect the performance. So it's kind of this cycle of interrelated, an interrelated relationship between these various entities. Typically, when you're talking to a non-material scientist, it's kind of like a foreign language. So I thought maybe we can do an exercise where you guys complete this thought. Material science is like a foreign language. You what? How might you complete this thought?
Learn.
You learn. You live. You live it. Okay.
Experience?
You experience it. I heard someone say material science is like a foreign language. You only use it when you're around other people that speak it, right? Or material science is like material science is like a foreign language. You only need it if you're in a country of people that don't speak English, right? So if you're a mechanical engineer and you're around all, you have a materials problem, then you suddenly need material science. But kind of to bring this analogy home, in 2008 I had a chance to visit National University of Singapore, and then I went up to Malaysia to visit one of my friends, and I got a chance to visit some of the universities there. Malaysia's, they speak Malay, but almost everyone speaks English, right? So I'm walking around, doing my sightseeing thing with the camera, and I got lost, and I found a guy who was doing some gardening, so I tried to get some direction from him. And so I asked him for direction. He said in very, very clear English, almost no accent, I don't speak English, right? It would have been like very, very helpful if I can speak just a few words in Malay. Why? Not so that we can have the conversation in Malay, just that he can become comfortable with me, and then he might have given me the information that I needed in the language that we both speak. So material science is kind of like that type of discipline for non-material scientists, right? If you're a mechanical engineer and you're working on some type of manufacturing process, and you have to talk to material engineers, then you should be able to understand a little bit of that language so that you guys can have the conversation to enable you to do the work that you need to do. So, as I mentioned, the name of our lab is Laboratory for Oxide Research and Education. The question might be asked, why oxide? I took this figure from one of the textbooks that we used when I was a graduate student at University of Florida, and basically it shows the wide opportunity that you have with oxide material. So if you take all of the physical properties that we have, like Young's modulus, electrical conductivity, thermal conductivity, yield strength, the electrical conductivity varies over the widest range, I'm pretty sure. Like, it varies over about 27 orders of magnitude. So for example, you have insulators, their electrical conductivity is about 10 to the minus 20 ohm centimeter. Or you can have superconducting materials that have electrical conductivity like 10 to the 5 ohm centimeter, right? So this is a pretty broad range. And across this entire range of this physical property, you can find oxides. So if you look at the insulators, we have the material that's typically found in glass or sand, SiO2, silicon dioxide. A common semiconductor that's getting a lot of attention is zinc oxide, basically a compound between zinc and oxygen. And then the superconductor materials that have like these very, very excellent current carrying capabilities. They're very complex, interesting compounds. This one, yttrium barium copper oxide, is what's called a high temperature superconductor, and that's something that's specific to the discipline because high temperature is still below room temperature. Basically what they mean is that you can use liquid helium to make this, to reach the temperature needed to make this material superconductor. So basically what you see is that oxides can be utilized, they have properties across this entire range. And so that means that by changing the structure of the material or changing the composition of the material, we can vary the properties of these oxides. So that makes them applicable to a lot of different technologies. So one of the areas that we're interested in is hydrophobic surfaces or water repellent surfaces. And I think you guys are all familiar with this type of image, right? You have lotus leaf, is found in nature. Basically, the structure of this material that is a naturally occurring structure makes the material naturally water repellent, right? Okay, so typically these types of surfaces, they need to have very, very low surface energy, and usually they have some type of roughness, like micro to nanoscale roughness. Normally these hydrophobic and superhydrophobic materials, they're polymers, right? So what are some properties of polymers that are intrinsic to these class of materials? So ME380 people should be like very good. I see several of you that are in the class, some of you have already taken it.
Polymers are tough.
They're what?
They're tough.
Are they tough?
They break easily.
They're not tough, right? They're
Not tough.
Yeah, they're not tough. I didn't hear the not part. So usually polymers have very, very poor abrasion resistance, right? And they typically are not very robust at high temperatures, right? So most of the hydrophobic and superhydrophobic coatings are based on polymeric type of materials. So for example, if you have a non-stick pan that you use for cooking, my wife always tells me don't use the metal spatula with the non-stick pan. You would think I would know that since I'm a material scientist. Sometimes in real life situations, you don't apply that knowledge, right? You should use the plastic because it has this Teflon coating that makes it hydrophobic, which results in this non-stick property. So if you have an application where you need to have a combination of hydrophobicity, wear resistance, and stability at high temperature, you're going to have a problem if you utilize polymers. So the way that this has commonly been engineered around is to make micro scale or nanoscale rough metal or ceramic type of surfaces. Okay? So recently there's been a discovery, I think this was in 2013, the citation is here, that there's a certain class of oxide materials that are intrinsically hydrophobic. Okay? Typically, the oxide materials are intrinsically hydrophilic. That means that the water typically easily wets the surface and it adheres very well, so it doesn't ball up like those water droplets that you saw on the lotus leaf. And so if we look at the chemical structure at the surface, so this is for like aluminum oxide, so we have this aluminum atom, then we have this oxygen atom. You can see that these empty orbitals that are those valence electrons, those outer electrons, they're easily accessed by the water molecule. So this water molecule can easily bond to the aluminum oxide surface, and that results in forming a sheet of water, so the surface will be considered hydrophilic. Whereas these rare oxide materials, what has been suggested in this paper that was published in Nature Materials about a year and a half ago, is that the outer electrons, those valence electrons, they're shielded by the core electrons, the 4s. So that means these have a filled shell. The ones that are inside, that are unfilled, that would normally participate in bonding, they're not available. So this water molecule has fewer sites that it can bond to. So the result is that the water balls up, it beads up, and the surface is hydrophobic. So we saw this and we were very, very interested because we work in oxide materials, and this is a very unique type of property. It has a lot of potential applications. You can use it in anti-icing, you can use it in self-cleaning materials, corrosion prevention, heat transfer, has heat transfer implications, so we became very interested in this. So basically we can characterize this tendency to be either water repellent or adherent to water by what's called the contact angle. And this is basically just a balance of these interfacial tensions. The main idea here is that we can get what's called a contact angle that's a function of these interfacial tensions. And if this contact angle is greater than 90 degrees, typically we say that the surface is hydrophobic. Okay? So one of our students, Fu, he became very interested in this area. So he made a lot of samples and he decided to test the contact angle as a function of these experimental parameters. And now I'm just going to show like his recent results, and then that will be the end of the presentation. Okay, so what Fu did is he coated a silicon substrate with cerium oxide, which is the main rare earth oxide. He did this by depositing the sample at different temperatures. So you heat the silicon up to either 200 degrees C, 400 degrees C, or 600 degrees C, and you do that either in the presence of oxygen. So here you have the pressure in the vacuum chamber is 30 millitorr of oxygen or 50 millitorr of oxygen, and the sample that says vacuum, these dark circles, is there's no added oxygen. Okay, so the way we make the sample is you put the substrate in, you turn on the vacuum pump until the pressure gets really, really low, right? And that allows us to make a very, very clean sample. So basically what we see plotted here is a water contact angle versus the deposition temperature at different oxygen pressures. So what you see is that 50 millitorr, this bottom curve, is pretty much flat, right? The contact angle is fairly low, and you can see the pictures here on the inset, right? Contact angle is about 30 degrees, between 20 and 30 degrees. So this is a hydrophilic type of surface that you will see for a typical oxide material. For the 30 millitorr sample, you can see at lower temperatures it's hydrophilic, and then the contact angle increases as the substrate temperature increases. And then the sample that were grown completely in vacuum, they're hydrophobic. So you can see here, the water droplet beads up on the surface, right? And this is stable. So after even 6 months, we remeasure these samples, you can see the same type of behavior. So one thing that is interesting is the capability to tune this property. So can you make it go from hydrophobic to hydrophilic? So in other work, people have shown different ways of tuning this by using applying electric current, by mechanically loading the material, like for example, Professor Yaron's group, they've stretched Teflon and it can show a change in the wetting characteristics. And some people have used UV light. So you shine UV light on the sample and that changes the wetting characteristics. So Fu decided to do that, and this is the first demonstration of tunable wetting of cerium oxide. Okay, so the previous slide I showed you, that's also fairly new data, but it's been proven before or suggested before that this material is hydrophobic. So now Fu is the first person that is suggesting that we can reversibly tune the wetting of this material. So what are we looking at here? So we see water contact angle versus time, and it's measured in hours. So the first data point is before shining the UV light, and then immediately shining the UV light, you measure contact angle again. You can see the water contact angle is really, really low. And then after some time, the contact angle starts to increase until it starts to saturate around 80 degrees, okay? And you can do this in a cycle, right? So basically we see here the cycle, so before UV light, after UV light goes down to about 25 degrees, then slowly comes back up to 80, and then goes down again. And he's done this for like multiple cycles, like 6, 8 types of cycles. So one question that he's trying to answer now is why does the contact angle not recover back to its original value? Okay, so this is kind of like the iterative nature of research. So he had a problem initially. He was interested in wetting characteristics of these materials. He tested it to see if this phenomenon is real. And he's like, okay, I have an idea. Let me see if I can tune the wetting. And now, after investigating that effect, he has some other things to look into. So he's done some subsequent experiments, and he's seen under some conditions you don't see this damping in the contact angle. Okay? So to wrap this up, our lab, we have expertise in synthesis of oxide films and nanostructures. I didn't talk about the nano stuff. We made various types of nanoparticles and nanowires. Through Fu's research, we've been able to demonstrate that the wetting of this rare earth oxide, cerium oxide, it has hydrophobic type of characteristics, and it doesn't have any type of micro or nanostructure. So if we were to make like micro pillars or nano pillars of this material, the contact angle would most likely go up, and it would be what's called super hydrophobic. So you have contact angle about 150 degrees. So we've also shown for the first time that this wetting can be reversibly tuned. So you can go from hydrophobic to hydrophilic and then back to hydrophobic by using UV irradiation. So in our lab, we have expertise for full characterization of the wetting properties of these films and nanostructured materials. We also collaborate with Professor Megarides and Professor Yaron, and also Professor Chakoudas in chemical engineering in this area. So we're looking at these materials for enhanced cooling of surfaces, dynamic control of wetting, anti-corrosion type of layers, anti-fouling, and those types of things. So you've been very gracious with your attention. Thank you for inviting me, and I hope that there was some benefit, and I hope to see you again.
Do you have any undergrad students working in your lab?
We have a lot of undergrad students working on that. Actually, I think we have four. We have five, I think. Last spring, we have 4 this semester. We had 5 last semester. So every semester we have undergrad students that work in our lab.
And what are the requirements to work in lab?
So the requirements to work in our lab is that you should be curious and that you should be self-motivated. Like, curiosity is important because that drives the work. Like, you should naturally just want to know how some things work or know more about a certain topic. And being self-motivated is important because I'm not going to call you or email you and ask you why you're not doing your work, right? I have a lot of work that every day when I go home, there's work that I probably could have spent another hour or two to do it. So the reason why we have that approach is because your work, doing your work is to my benefit, of course, but it's primarily to your benefit because you're enhancing your skills, you're enhancing your knowledge, you're enhancing your expertise. So those are 2 main criteria, that you should be curious and that you should be self-motivated. Typically, if an undergrad student approaches me about undergrad research, I assume that that student is already curious and self-motivated, so we accept them unless there are space limitations. The last 2 semesters, we've had to turn away students because there are just too many students that were interested.
And let's say I was interested, or anybody else, in working in your lab. Now, would that be too late to join?
This semester we have 5 students, and we try to keep it at 4 or 5. Maybe next semester we might do 3 or 4. So it's too late for this semester, but maybe we can talk in a month or so about next semester.
Okay.
So we have some students doing it for undergrad research with credit, and then we have some students that have been working for 3 or 4 semesters that are just doing research.
Does anybody have any questions?
Where do you guys get more information about the next semester to join the lab?
Okay, just email me. My email is at the bottom here. It's fairly easy, JTA. JTA. T is in Tom, or Terrell, which is my middle name, and A, Abiade, JTA@uic.edu. Or you can just stop by my office. I'm in 3049 ERF. Generally, I have an open door policy. If I'm there and you have a question, you can stop by. If I'm in the middle of something, then we'll have to make an appointment to discuss, which you can come by and talk. And if you go to the MIE department website and click on my faculty webpage, you can see like more details on other projects.
Thank you.
Any more questions? All right, thank you very much. We have more ice cream left, so go get it before it's gone. Guys who are on the team, stick around. I want to have a short meeting with you. Otherwise, we'll see you.